Okay, we're gonna pick up here. We are on chapter 9. So last time we got into solutions, and remember, solutions are the substances that get the aqueous symbol next to it. Ultimately, what it means is a water environment. It really is a homogeneous mixture. So it's a mixture basically of two things, and that's why there's two parts to a solution. There is the solute, which is the smaller part of the solution, and there's the solvent. And both of those things together, which is obviously the larger part, make up a solution. And again, an example like we talked about last time is you have H2O, which is a pure substance or a pure liquid, and you put it together with some sodium chloride. That salt will dissolve in the water and it will make a sodium chloride solution that is aqueous. And again, that is the difference between something that has the L symbol or liquid symbol and something that is aqueous. Although they are both in sort of the liquid state, something with an L is just a pure substance. So water just like by itself, nothing else there. Again, a solution is really a mixture of two or more things, usually two things, where we have the solute and the solvent. We talked a lot about sort of solubility and how sort of molecules interact with each other. And really, intermolecular forces is one of the main sort of reasons are how things interact with each other. Intermolecular forces are the forces that hold together, two molecules, basically. That's like how a molecule and molecule interact. And all intermolecular forces are always weaker than intramolecular forces. And intramolecular, I spelled that right. I got the forces too soon. Molecular forces. Intramolecular forces are really the force that holds one molecule together. So what is the difference between that? For example, if we look at just one single water molecule, an intramolecular force is the covalent bonding that's happening between the oxygen and the hydrogen, the sharing of electrons. So within that one molecule, those covalent bonding is basically an intramolecular force, is what holds that water molecule basically together through the sharing of electrons. Intermolecular forces is the force that holds, for example, this water molecule together with another entire water molecule. And as we talked about, water is polar and the oxygen is more negative, the hydrogen is more positive. So these guys are held together by an intermolecular force, which, as we talked about last time, is hydrogen bonding. And hydrogen bonding is a relatively strong intermolecular force. Now, intermolecular forces, as I mentioned, are always weaker than intramolecular forces. And a very simple example of how we know that's true is basically water itself. So when you take water and you want to cook some pasta, right, and you start to boil it, when you start to do that, it's actually the bond between the two water molecules here that breaks first when you start to boil. And then it allows those guys to kind of go off into the gas phase as it starts to boil. If it was the other way around, when you would go boil that water, you would break these bonds and you would start to produce hydrogen gas and oxygen gas. And you probably wouldn't get to the part where you put the pasta instead of water or anything like that, because that would not be a good situation. Thank you. So, intermolecular forces are always weaker than intramolecular forces. Typical intramolecular forces are covalent bonding, ionic bonding. Those type of bonds just hold the molecules, basically individual molecules, together. We talked about three types of sort of intermolecular forces as we were talking about sort of solubility. We have hydrogen bonding, which is, again, a bond between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine. And that's what allows something to have the ability to hydrogen bond, is you have to have that actual bond there. You actually have to have in the molecule a hydrogen that's directly attached to a nitrogen, oxygen, or fluorine in order to create a really polar bond. And that's going to give it like that positive side, negative side. And this is typically the bond intermolecular forces that polar molecules use with other polar molecules. that obviously have the ability to hydrogen bond. An example is what we just saw there in the previous slide, basically water with water, basically. They both can hydrogen bond. By the way, as we also talked about, pretty much all intermolecular forces are just an interaction of the positive side of one molecule is attracted to the negative side of another. So that's basically all how all intermolecular forces basically work. Just a simple sort of positive side and negative side attraction of those molecules is what holds that together. That's probably your strongest sort of intermolecular force. Next is what is known as dipole-dipole interaction. And again, this is also for polar molecules, but these are polar molecules that cannot hydrogen bond. So these are polar molecules that don't have the ability to hydrogen bond. This is how they work. And what we talked about in sort of our bonding chapter is if a molecule is dipole moment, which basically means there's a negative side of the molecule. So basically this type of interaction is pretty much what I drew below. You will have a positive negative side to this polar molecule, and you'll have another polar molecule that has a positive negative side. And again, that is how they're going to interact with each other. And it really is the same type of interaction that we see in water, as hydrogen bonding is a dipole-dipole interaction. And in between here, that's a negative, badly negative zone. But it is basically a dipole-dipole interaction. So an example, maybe something like, this guy here, which would be a polar molecule. It can participate in dipole-dipole interaction, but it cannot participate in hydrogen bonding. Once again, as we talked about last time. Oh. Apparently. Let's start that thing back up. All right. Sure here. Okay, so this type of interaction, once again, this guy here, even though again it's a hydrogen involved, it cannot hydrogen bond. So I think we talked about it last time, just because there's a hydrogen there, it doesn't allow it to hydrogen bond. And that's because that hydrogen is not directly attached to a nitrogen, oxygen, or fluorine. So it has to be on those three elements for it to have the ability to do so. In fact, that carbon-hydrogen bond is non-polar, which means it doesn't have a charge at all, right? It's not like positive side or negative side, so it can't do that positive-negative attraction. The last type of sort of intermolecular force that we touched upon was dispersion forces. And really, these guys are for non-polar molecules and non-polar molecules. This is basically how they interact with each other. And these are the weakest of all of them. And that is because, again, a non-polar molecule and another non-polar molecule, they're essentially neutral, which means out of the box, they don't have a way to do like the positive negative attraction because they have no charge. So they have to have something occur to them to allow them to interact. And one of the things that can happen, as we talked about there briefly, was all the electrons in one of these nonpolar molecules could all just end up on one side of the molecule versus the other. And that's going to, again, temporarily here create a charge in that nonpolar molecule. And because this nonpolar molecule is now next to this other nonpolar molecule, the electrons in this guy is going to be now attracted to the left-hand side here and that positive charge. And now that second nonpolar molecule, which normally doesn't have a charge, will also gain a temporary charge. And now both of these guys that started with no charge temporarily have a charge and really a way to interact with one another. It is temporary because eventually, like I said, I think last time, the electrons will go back and kind of move back out of that position, and it's going to lose that temporary charge, and it won't be able to hold on to, that attraction. And that's why it's the weakest out of all of them. So these type of interactions are really what allows things, for example, to be soluble in each other or mix with each other. And we have that idea of like dissolves like. And the idea of that is things that have basically similar intermolecular forces that the other molecule has, and they share similar intermolecular forces, they're going to be able to interact well with each other. So if some molecule here can hydrogen bond with itself, it can also hydrogen bond with water that hydrogen bonds with itself. So they're going to have no problem interacting with each other. If something is using a dispersion force normally, and something else uses a dispersion force, they also are not going to have any trouble because, again, that's a similar type of interaction. So they're going to mix. By the way, the strength of dispersion forces, speaking of that, does increase with molar mass. And the sort of larger the molecule, the stronger that weaker force is, that dispersion force. And the reason for that is with greater molar mass, that means you have more atoms. More atoms means you have more electrons. So you have a greater opportunity for those electrons to kind of move around and create that temporary charge that's necessary for that interaction to occur. So what this like dissolves like means is, again, ionic things and polar things, they're going to be good to go. They're going to be soluble and mix. Again, polar things and polar things will also be soluble. Also, nonpolar things and nonpolar things will be soluble. Again, you, for the most part, only kind of run into trouble, as we talked about, if you cross over polar and nonpolar. That is going to be not so good. They're going to be insoluble in one another, again, because they're not going to have that interaction between each other that can basically hang on to that for a long period of time. For a short period of time, they're going to be okay, but eventually, I think I talked about oil and vinegar salad dressing the other day. Eventually, things will just kind of move apart from each other because they won't be able to maintain that sort of interaction. Any questions on any of that stuff there? Yeah. All right. So now we kind of have a little idea about solubility. How do we know, for example, if we do a reaction, say like a double displacement reaction, we put two ionic compounds together, would we expect maybe a solid to form or not to form? And one of the ways we could kind of predict that is what is known as solubility rules. And solubility rules help us decide whether or not when we kind of throw two things together, these two like ionic compounds, a metal and a non-metal, would we expect them to basically make a solid or not make a solid? And when we talk about solubility rules, if it is going to be if it's going to be soluble, it will get that aqueous symbol next to it when you kind of write the formula and you write it in an equation. If it is insoluble, that means you will get a solid that's formed, and it will typically get the solid symbol next to them. So some of these rules here are, if you have anything in group 1 on the periodic table, you're good to go. That's going to be soluble, so that's not going to make a solid, and it really will be a solution. If you have anything that has ammonium in it, NH4 plus, that also will be soluble. There are no exceptions. And if you have anything with nitrate, also going to be soluble, no exceptions. So there are no exceptions to that. So what that means, if you're looking at a chemical formula, something that's ionic, and you want to know, is that going to be like a solution or is that going to be a solid? As soon as you see any of those things in the formula, it's going to be a solution. It's going to be soluble. You won't have a solid that will form. Now, if you have anything that's chloride, bromide, and iodide, those guys will be soluble in everything. But there are actually 3 exceptions. And the 3 exceptions are silver, lead 2, and mercury 1. And what that means is normally these guys over here, these guys are going to be aqueous no matter what the situation is. These guys are going to be aqueous, but if you have one of these 3 with any of those, they will not be aqueous. They actually will make a solid. So that's sort of what the exception means. It's basically the opposite is going to occur. If you have sulfate, it's typically going to be soluble, except if it's one of these kind of 4 guys, then it will be insoluble and you would expect a solid to form. Now, there also are some things that are typically insoluble, which means these things typically are going to be solids when they kind of come together. Carbonate here is typically a solid, except if it's with group 1 or ammonium, then it would be aqueous. Phosphates are typically solid unless, again, it's with group 1 or ammonium, which is basically our very first rule up here, basically, these two. And it would be aqueous. And hydroxide is usually solid unless it's with group 1 or strontium and barium, and then it would be aqueous. So how do we use this rule? Let's say we take a double displacement sort of reaction like something. Let's go with sodium chloride plus a little silver nitrate. This is a positive negative, right? Positive negative, definitely a double displacement. Gonna switch partners. And when they switch partners, we will get NaNO3 and we will get AgCl, right? So if we want to know sort of what is like the states of all these things, we could use these rules to help us. So I'm going to take a look here at the very first one. That is sodium, and that is group 1 on the periodic table, which means it's always soluble. Oops, come back, come that way, maybe. There you go. There are no exceptions here, which means as soon as I see the sodium, I'm good to go to write aqueous next to that. I know that should be a solution. It should not be a solid. I come over here to the next one, which is silver, which may not be on my list on the left, but the second guy that's nitrate, which is right here. And nitrate is soluble in everything. And once again, there are no exceptions. So as soon as I see the nitrate in the formula, I know that this also is going to be a solution and have the aqueous symbol next to it. Any questions on that there? Coming to the other side, I see sodium, which honestly is as far as I need to look because that is group 1. There's no exceptions. I know it's going to be aqueous. If you were not convinced, you could still look at nitrate, which also is soluble in everything and has no exceptions. So they both tell you the same thing. They should. That means that we come to our last one where we may not see silver on the left, but we do see chloride. So chloride's right here. It is typically aqueous, except when it's with silver, lead, or mercury. And in this case, my chloride is actually with silver. And because that's an exception, instead of it being soluble, here we would actually expect a solid to form. And this would be insoluble. It's actually a white solid. And you would get this solid that would form in this case. So that is how you could kind of use these rules to determine, what would be your solid if you had like a precipitation reaction, what would not be a solid, what would be a solution. Any questions on that there? So why don't you try one here? Let's do something. Let's do PbNO3 plus a little Ki, and that's gonna make PbI2 plus some KNO3. I'll balance it like I'm in chemistry class here. Maybe there we go. All right, so based on the rules there, fill in what the state should be. I'll give you one more maybe. Let's do so again, if you can't find one thing, you should hopefully be able to find the other thing in the formula. So here again, we may not find lead on the left, but we will find nitrate. Nitrate's right there. It is soluble in everything. Again, there are no exceptions, which means as soon as I see that NO3, I know it's going to be aqueous in a solution and not a solid. Here we have potassium, which is group 1 on the periodic table, also soluble in everything. There's no exception. So again, as soon as I see the potassium in that formula, I know it's going to be aqueous and again, a solution, not a solid. When I come over here, again, may not see lead on the left, but I do see I, and I is soluble in everything except for these three. And lead happens to be the exception, one of the 3 exceptions. So instead of being soluble, it's going to be the opposite. And this would actually make our solid in this case. And that's going to be our solid guy here. Little yellow solid precipitate making. Lastly here, I see potassium or nitrate, your choice. They both are soluble in everything, and they will be aqueous in this case. So this would be a precipitation reaction where the precipitate that's made is actually the PbI2, and it's coming from the Pb2 plus from the lead 2 nitrate, and the I minus are coming together, and it's going to drop out of solution as a solid, because they won't mix, basically. Yeah. Any questions on that one there? Coming next, I see barium chloride. I see chloride is soluble in everything except for these three. And in this case, barium is not one of those three. So that means it is going to be soluble and aqueous here in a solution. I see sodium, which is group 1, and that's again as far as I need to look because there are no exceptions for group 1. And that means that that is going to be aqueous as well. Over here, once again, I do see sodium, same response there, group 1, soluble in everything, no exceptions, going to be a solution. Lastly, barium sulfate. And barium here, where is sulfate? There it is. So sulfate's right here, which is typically soluble except for barium. And that means it's going to be the opposite. So this is going to be our white solid that would form, which is barium sulfate in this case. Any questions on that there? No. If you need them, you just need to know how to use them if they're provided to you. Yeah. Other questions? All right. So now we understand how we get some of those things. Let's take a look at a couple other things about solubility. So we talked about some solutions and solubility and a couple of things. This idea again of like dissolves like is really one of the big things in terms of solubility. And it's really based again on those intermolecular forces. Also, those intermolecular forces, as I might have mentioned last time, is also the reasons why certain things have, for example, higher boiling points than other things, or higher melting points than other things, how they interact. The solubility of a solute does depend on temperature. So there really is, at a given temperature, for example, only a certain amount of solid you could get to dissolve. So usually if you raise the temperature, you'll have a larger solubility of a solid in a liquid. So a lot of times if you have trouble dissolving something, sometimes they tell you to heat it up, and that allows you to kind of dissolve it a little bit more. At lower temperature, you have a larger solubility of a gas in a liquid. So gases fly around based on energy, right? And if you lower the temperature, there's less energy. And that means your gas molecule, dramatically drawn here, is going to be flying around a lot slower. And that means it's going to stay in the liquid part for a lot longer period of time, and they will stay mixed for a lot longer period of time because of that. Obviously, the opposite is true, right? If you increase the temperature, your gas molecule is going to probably fly out a little bit faster in temperature. Speaking of gas, it is related to pressure. The higher the pressure, the larger the solubility of a gas in a liquid, for example. Also, and just with gases itself, and that's Boyle's law relationship. With Boyle's law, as the pressure goes up, the volume goes down, and vice versa. Pressure goes down, the volume goes up. So what happens, obviously, at a high pressure, you have a small volume. And in that small volume, obviously, you have a lot of the gas molecules near each other. And just by that proximity, they're going to just continuously mix because they don't have a lot of room to fly around in. So it's going to constantly be mixing. Opposite solubility would drop a little bit as you lower the pressure and the volume gets larger because everybody has a little bit more room to kind of fly around in. Now, when we talk about solutions, there's a couple different ways that we classify a solution. One of the ways is what is known as a saturated solution. And if you have a saturated solution, what that means is at that given temperature, you pretty much have gotten everything to dissolve in it. So you've gotten the maximum amount of like solid you could dissolve in there. So for example, if you're dumping like sugar into some water, you could keep adding sugar, mixing, it'll dissolve at some point, right? If you keep mixing and keep adding, it's not going to dissolve anymore. So it's going to kind of pile up on the bottom. And at that point where it stops dissolving, you have a saturated solution. What is the opposite of that? It's what's known as an unsaturated solution. In an unsaturated solution, you haven't hit that point yet. So you could continue to dissolve that solid, and it will continue to dissolve until you hit a saturated solution. So, if you have like a small sugar packet in some water, you dump it in there, it'll dissolve. You can put some more sugar in and more sugar in. And you can continue to do that until you hit a saturated solution. And at that point, no more will dissolve. There's also a third type of solution, which is sometimes referred to as a supersaturated solution. And basically, how you make a supersaturated solution is, for the most part, you take a solvent like water or something like that, and you heat it up. And as you heat it up, you put a bunch of solid in there to dissolve. And when you're doing that, you're going to get a lot more solid to be able to dissolve at that higher temperature, as we just talked about, because you're increasing the temperature. So it's going to allow a lot more solid to dissolve, for example, in the water. And once you get a bunch of solids sort of dissolved, this is really hot temperature. What you do is you kind of kill the fire there, and you kind of just let this solution cool back down. And when it cools back down, a couple of things happen. It's still a solution, so it's still in the aqueous sort of symbol. It's still a solution looking. All that stuff still dissolved in it. The problem is when it drops back down to a lower temperature, the solubility of what you just dissolved in it changes. And now what you have is a solution that has way too much solid dissolved in it at that lower temperature, right? You're able to do it because you heat it up, get it all dissolved, let it cool back down. And what it actually creates is a really unstable solution. It's so unstable that, frankly, if you just put like a speck of whatever you dissolved in there, just like a super small speck of whatever you dissolved into that solution, and you just drop it in, that is enough for it to go, whoa, I got like way too much dissolved. And what will happen is it'll go from the liquid state, which is a solution, and it will, all the solid will then just come right out of solution. And it'll go kind of from the solution to like a rock hard solid because you kind of tipped it over. It's actually so unstable a lot of times, you don't even have to add the thing. If you just actually tap it too hard, it will just come out. I had many demonstrations where I go do that, and it's just moving the flask is enough to disturb it and have all the solid come out of solution, stuff like that. So that's a supersaturated solution where you have way too much solute dissolved in a solvent at a given temperature, and it's usually fairly unstable, and usually will want to precipitate out as a solid in that case. Other ways we describe solutions is concentrated or dilute. In a concentrated solution, it contains a relatively large amount of solute, so the stuff dissolved in the solution. In a dilute solution, it contains a relatively small amount of solute. You usually will have more solvent than solute, so you have a little bit more like water, for example, than you do of the stuff that's dissolved in there. So usually when you buy solutions or chemicals, they come concentrated. And like when you use it in a lab, they dilute it down with some water or whatever it may be, and it's a little less strong, if you will. Kind of like, again, if you got a cup of a drink with some ice in it right before you came to class and left it in your car. Afterwards, you come back, right? All the ice melts. Doesn't taste as good, right? It's a little bit more diluted, not as strong as it was, right, when you went to class, because you now added a lot more water when your ice melted, right? A lot more solvent, and it really diluted it down. Any questions on that there? You still take a drink, right? Just to see how bad it is, right? Just to see, Then you're like, oh, maybe I shouldn't have done that. That's not so good. All right, any questions on that there? Next thing we're going to talk about is actually electrolytes. And electrolytes are substances that dissolve in water and produce ions and conduct electricity. So an electrolyte is a substance that can produce ions, and that's really important here for the second part of it, which is to conducting electricity. So the presence of those ions, the positive ions and negative ions in solution, is what helps kind of complete the circuit and allow it to conduct electricity. So there are strong electrolytes, and if you have a strong electrolyte, it will 100% break apart into ions. So if you take something like, for example, sodium chloride, that is a sodium chloride solution. In a sodium chloride solution, it will 100% break apart into sodium ions and chloride ions in that beaker or whatever you may have, sorry, in that test tube. So if you had sodium chloride solution, you really have none of the sodium chloride units together. It will 100% break apart into those ions. You have none of these units together in the solution. And because there is just a lot of ions in that solution, this can conduct electricity really well. So this conducts electricity well. So there's like a light bulb type of experiment where you take a light bulb that's got some electrodes attached to it and you put it into different solutions and you put those electrons into a strong electrolyte solution. It's going to be very bright. Yeah, it's going to turn on. And it's going to be very, very bright. Going to have no problem conducting electricity. And you'll have a lot of light that will basically happen. Pretty much all ionic compounds are strong electrolytes. All ionic solutions are strong electrolytes. Strong acids, like these list is some strong acid, hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, hydriodic acid, and sulfuric acid. These are all strong acids or strong electrolytes. They completely break apart in solutions. They do not stay together. All you get is a bunch of ions in there, which will conduct electricity really well. Also strong bases, and a lot of strong bases come from group 1 and group 2 on the periodic table, like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. These guys also are strong electrolytes and will completely break apart in solution, conduct electricity really, really well. Any questions on that there? So for example, if you had hydrochloric acid in solution, when you have a hydrochloric acid solution, you have none of the HCl units still together. You have, again, 100% of these guys in there. And if you looked in the beaker, that is pretty much what you would see is just these guys. You would have none of these units still together. Any questions on a strong electrolyte there? Now, a weak electrolyte is also a type of electrolyte. And a weak electrolyte will actually mainly stay together, but will produce some ions. So because it's able to produce some ions, it's still able to conduct electricity. So it can still conduct electricity, but nowhere near as good as a strong electrolyte. So if you take that light bulb example and you put that guy into a weak electrolyte solution, it would turn on, but it would look very dim, like it's kind of dying almost, but it would still kind of turn on, but it looks like it's just about ready to kind of lose power, if you will. And it's still able to conduct electricity because there's still presence of some ions in that solution. Most weak electrolytes are weak acids, which is pretty much all acids other than that list I just made on the other page, like hydrofluoric acid, acetic acid, like in vinegar, list goes on, HCN, and so forth. So if you have something like hydrofluoric acid, it will also break apart in solution into H plus and F minus. The difference is when you look at that beaker, you're going to mainly have HF units still together. And you have just a little bit of some free ions in that solution. So it's going to mainly kind of stay together. So it's going to kind of stay here together mainly. But you will get a little of these ions in solution. And again, because it's still able to create just a little bit of ions, it's able to conduct electricity a little bit Again, not anywhere near what a strong electrolyte could. We also see something different in this type of reaction, which are these reversible arrows. And when you have reversible arrows like that, it basically means that this reaction is actually not like a one-way street, it's a two-way street, and it goes in two directions. It goes from reactants to products, which is known as the forward direction. And then at some point, once you start making some of these products, they actually will come back together and combine and go back the other way. And you have what is referred to as the reverse direction, which is why the arrows are heading in both directions. It's basically a two-way street. This will eventually come to what is known as chemical equilibrium. And what chemical equilibrium means is it doesn't mean equal like the name kind of implies. It doesn't mean you got equal amounts on both sides of the arrow. What it's actually referring to is at some point the rate of the forward direction will equal the rate of the reverse direction. So basically what that means is just as quick as it goes this way, it's just going to come back the other way just as quick. And what that does is essentially locks everybody into place in terms of where they're at, right? So if everybody just locks in terms of their concentration, if you go this way and this way at the same rate, nothing really changes. Everybody just stays where they're at, basically, until you do something to screw it up, which we'll talk about in a later chapter. But it basically will just be able to maintain where they're at indefinitely, really, in this case. So again, weak acids, also weak bases are weak electrolytes as well. Probably the most common weak base you'll come across is ammonia, NH3. A lot of nitrogen containing things, organic things are weak bases, but that would be that. So how do you recognize the difference between like a strong electrolyte and a weak electrolyte? Well, the arrow is a big key there. You got double arrows, going to be a weak electrolyte. Also, if you visually see something like, again, the light bulb is very dim or not conducting a lot of electricity, that again is going to tell you it's weak. How you know it's a strong electrolyte, you usually should always have a one-way arrow heading towards the product side, and again, should conduct electricity really, really well and be very, very bright. Any questions about that? The last type of electrolyte is a non-electrolyte, and a non-electrolyte will dissolve in water, but not create any ions. So it's able to dissolve in water, but not create any ions. And common example would be sugar, right? You can have some sugar, you can put it in some water, and you'll end up with sugar that's dissolved in a solution. The deal with sugar is it's carbon, hydrogen, and oxygen, and that is all covalently bonded, no ions, right? So this guy is still covalently bonded on this side. And because you get no ions means it will not conduct electricity. So if you put that kind of light bulb into a non-electrolyte solution, the light bulb pretty much will not go on. It'll just basically stay off. And that's because, again, it's not conduct electricity. Also, by the way, if you take that light bulb and you put it into solid sodium chloride, it will not conduct electricity either because the ions are stuck together. They have to be floating around in solution in order for it to be an electrolyte and conduct electricity. So you would have to dissolve that solid sodium chloride into a sodium chloride solution. Now you'll be able to conduct electricity because you have those ions floating around in solution. But if you just stuck it like in the solid, no water involved, it will not conduct electricity. So how do you know it's a non-electrolyte if you're looking at an equation? Well, you got the same thing on the left-hand side and the right-hand side, yeah, and there's no ions, yeah. So that is how you know it's a non-electrolyte. Yeah. Any question on those three there? Yeah. By the way, pure water, is it a good or bad conductor of electricity? It's actually a bad conductor of electricity, right? And that's because water is covalently bonded. There's no ions. Just so we're clear, the water comes out of your pipe is not pure water. Yes, it is a lot of ions in that water. It will electrocute you. So don't, blow dry your hair in the shower or anything like that. But they actually put ions in there to clean it. So there is a lot of ions in there. But if you have pure water, H2O, no ions involved, no deionized water, for example, it should not conduct electricity again because there's no presence of any ions that are present. Again, once again, safety note, the water coming out of your pipes is not pure water. Yes. Here's our light bulb example there. Again, at the very top, what we see is sodium chloride. solution. Ions fully breaking apart. You can see the light bulb shines very, very brightly. Again, an indication that that is a strong electrolyte. Here's our HF, which is our weak acid and weak electrolyte. As you can see in sort of the picture there, mainly HF units still together. A little bit of H pluses and F minus in that solution, so still able to conduct electricity. So as I mentioned before, you can kind of see it will turn on, but it'll be very, very dim. Not able to conduct anywhere near the electricity that obviously a strong electrolyte can. And obviously, lastly, here's our sugar example. And you can see the light bulb does not go off again because there's in the presence of no ions in that solution. Any questions on any of those things there? Okay. Next thing we're going to talk about then is equivalence. And equivalents are, for the most part, a way that sometimes solutions are concentration of solutions or like IV bags are given to you. And equivalents are related to the charge of the ions that are present. And there's two common sort of units that we sometimes will use for like a concentration unit of a solution in equivalents, and that is equivalents per liter or milliequivalents per liter. And those are kind of two sort of units that are sometimes used. Milli conversion here is the same one as like milliliters to liters. So, right, there is 1,000 milliliters in 1 liter, which would mean there is 1,000 milliequivalents in an equivalent, right? So that's kind of the same conversion as our milli conversion. So, for example, we could use the actual charge of the ions that are present as a conversion factor to allow us to calculate these type of units. So if we had a sodium ion, the sodium ion has a +1 charge, and doesn't really matter, for example, if it's a positive charge or a negative charge in this case. What we're looking at is actually just the number. So the number is actually what's important here. And we could come up with sort of a conversion factor that 1 mole of sodium ions will give me 1 equivalent. And the 1 equivalent comes from the +1 charge here, basically. If we had something like calcium that's +2, that is a 2 charge there. And we could say 1 mole of calcium ions gives us 2 equivalents in this case. So we could use the actual charge as sort of a conversion factor. And like I said, it doesn't matter if it's positive or negative. So if you had something like, we'll do chloride here. And basically has a -1 charge. So 1 mole of chloride ions would give me 1 equivalent. If you had something like sulfate, -2, 1 mole of sulfate will give me 2 equivalents. So again, we need them for example, a conversion that we might want to do. So for example, let's take a look at a unit of concentration that is common to us, and we'll see in just a second, and that is really moles per liter. And moles per liter is what is known as the molarity of a substance. And that's a very common sort of unit of concentration that is used, probably the most common unit that's used. So for example, if I had a 0.025 moles per liter of a sodium sulfate solution, right? And I wanted to figure out basically what is the units in equivalents per liter or milliequivalents per liter, each of the ions that are present in this case. So when we look at sodium sulfate, it is going to break apart into 2 things. You will get 2 sodium ions, right? Because that's going to break apart when it goes for a swim into 2 sodium ions. That's basically what that 2 means, right? And we will have one sulfate ion, basically, when it goes for a swim there. Now, how molarity sort of works is it's kind of like stoichiometry. We could use the mole to mole relationship for these things. So, for example, for every one of these whole things that I have, actually, I'll move it down here, 0.0250 moles per liter. For every one of the whole entire sort of ionic compound that I have there, get rid of that there, I get not one, but I get two of these sodium ions, right? So it's like a 1-to-2 relationship. You get twice as much sodium for every one of those who go for a swim. So how that affects this concentration is you actually need to multiply it by 2 to get the proper concentration of your sodium ions in that solution. And if I do that, I will end up with maybe a calculator here. 0.05 moles per liter. And that would be the concentration of the sodium ions in this particular case. And again, it's really just like stoichiometry. For every one of these, I get 2 of these, twice as much in there. So you have to multiply the concentration by 2. Now, for every one of the whole things, how many sulfates do I get? I get 1. Yeah, it's a 1-to-1 relationship, which means if we're looking at just what is the concentration of just the sulfate ions, it would be basically 1 times the whole thing's concentration, which obviously will still equal the same number, 0.0250 moles per liter for my sulfate here, right? So these are the concentrations, for example, of our ions as they're floating around in that solution. And just visually, here's the deal, right? When you do this and you dump in your sodium sulfate and it's going to break apart because it's ionic, you get 1 and 2 sodium ions for every 1 sulfate, right? So again, you get a 2 for 1 special, yes. So twice as much of those guys as it is sulfate basically floating around in the solution. And again, that is why the concentration of sodium is twice as much of the other guy that's floating around. Concentrations are not additive, so they don't add up to the original one. It's sort of like proportion of what you got going on in that solution. So now that we have the concentrations of each of these ions, we could actually change these into our other units of equivalents per liter and milliequivalents per liter. So we'll start with the sodium. And what we know about the sodium ion, like we saw on the previous page, is it has a +1 charge, or really a 1 charge. And that means the conversion factor we could use is for every 1 mole of sodium ions, there is 1 equivalent. And we're really just going to use that as a conversion factor. So we'll take our concentration of our sodium ion by itself. And again, we're going to do dimensional analysis here. So moles are on top, so we want moles on the bottom. So 1 mole of sodium gives us 1 equivalent here, right? Again, multiplying and dividing, the moles of sodium will cancel, and that will get me 0.05 equivalents per liter. And I have now just converted this into that unit right there. Any questions on that there? Now, if I want milliequivalents per liter, we're just going to use our conversion, which is, again, there are 1,000 milliequivalents in 1 equivalent. So again, we're going to go opposites to cancel. Equivalents are on top. On the bottom would go 1 equivalent and 1,000 milliequivalents. And again, that's going to cancel. That's going to cancel. And that will then get us to basically 0.05 times 1,000 will give us 50 milliequivalents per liter for sodium ion. Any questions on that calculation there? Now, that will give us basically what this concentration really is based on the charge, right? So there's an ionic compound, got different charges, everything needs to be balanced, right? So what we have now is really the charge here of our positive guy floating around in there. We could do it for our negative guy, which is our sulfate. So when we look at sulfate, like we saw on the previous page, its charge is 2, which means for every 1 mole of sulfate, there is 2 equivalents. And once again, it's just the number. It doesn't matter if it's positive or negative. So in this case, we're just looking at the number of the charge. So we will start with the 0.025 moles per liter of sulfate. We'll do our dimensional analysis here. Again, we want moles on the bottom. 1 mole of sulfate is 2 equivalents. Again, the moles of sulfate will cancel, and that will give me 0.05 equivalents per liter of sulfate in this case. And that's obviously sodium up here. And once again, we can use our equivalents to milliequivalents conversion to take it to milliequivalents. And again, in 1 equivalence, there is 1,000 milliequivalents. And that's going to get me 50 milliequivalents per liter of sulfate. And now we have the concentration of the negative guy floating around. First off, any questions on the calculation there? Are they the same or different? They're the same. They're the same because when we put an ionic compound together, right, we make sure the charge equals 0, right? And that means that really all the positive guys floating around in terms of their charge and all the negative guys floating around, they balance each other in terms of what's floating around in that solution. And that's ultimately what should always happen in an ionic compound. So if you have an ionic compound solution, you have to calculate either of these concentration units for the positive ion and the negative ion. You should always end up with the same equivalents per liter or milliequivalents per liter, because an ionic compound should always be balanced out to 0 in terms of its charge, and they should always end up the same. Any questions on that there? Why don't you just try one here? We'll just do, let's say we had 0.015 moles per liter of phosphate. And we want to know, again, what is the units in equivalents per liter and milliequivalents per liter. So why don't you give it a go? All right, so let's take a look. And again, we want to basically go from moles per liter, which is molarity, to equivalents per liter. So the bottom's good. We really just got to go from moles to equivalents here. And again, it's the formula that's going to allow us really the conversion factor to do that. And once again, it's really just the number of the charge, doesn't matter positive or negative. So what we see there is for every 1 mole of phosphate, we do get 3 equivalents in this case. And again, it's the actual number there of the charge. So we're going to use that again as a conversion factor. We'll go 0.0150 moles per liter of phosphate. Again, opposites cancel, so moles on the bottom here. And 3 equivalents up on top. Again, the moles are going to cancel. And that's going to leave me my equivalents per liter about 0.045 equivalents per liter of phosphate in this case. Any questions on that there? At this point, we're just going to convert it really. It's just the kind of milli conversion from equivalents to milliequivalents. And again, here, as we saw previously, in 1 equivalent, there is 1,000 milliequivalents. So that's going to get us to about 45 milliequivalents per liter here of phosphate. Questions on that calculation there? Yeah. I would say those are, for example, two very common units when you do this type of calculation, equivalents per liter or milliequivalents per liter. So it could be one or the other, but those are two of the common ones and stuff like that. So sometimes like IV bags and stuff like that will have those, so kind of equivalents per liter or milliequivalents per liter and stuff like that. Other questions? So as we saw there, a lot of body fluids typically contain a mixture of several electrolytes. And again, an equivalent is the amount equal to 1 mole of its positive or negative charge. And as we can see here in this table, it doesn't matter, again, if it's positive or negative, really just the number gives us our equivalent amount in this case. All right, why don't we take a 5-minute break and we'll continue on. So the first one we're going to talk about, there are a few different sort of percent concentration units, and the first one is mass percent, sometimes abbreviated with a percent m/m, which does mean mass to mass percent. And to calculate the mass percent, you take the mass of the solute, which again is the smaller part of the solution. You divide it by the mass of the solution. So typically these are like grams and grams, and you times it by 100%. That gives you sort of a percentage. Now, really, the important part for sure with this sort of formula is actually the bottom here. And the bottom, which is the mass of the solution, is really important because you want to make sure that you get both parts of the solution. So you do want to make sure that you do get both the solute and the solvent. And the reason that's really important in these type of problems is very traditionally, they will kind of separate out those numbers for you. So they'll kind of give you the mass of the solute by itself, and they'll give you the mass of the solvent by itself. And it's a very common error that people will make is they'll just grab like the solvent by itself and kind of divide by that because it's a larger number. So you want to make sure on the bottom here that it is the actual mass of the entire solution, which again should be both the solute and the solvent added together. So that's really important there. By the way, if you have a percent concentration given to you, like if you had a 4.5% by mass sodium chloride solution, you could actually turn that into, for example, a usable conversion factor. And basically what that means is you would have 4.5 grams of sodium chloride in 100 grams of solution. And you could use it as a conversion factor. You could also flip it around and do a dimensional analysis if you needed a solution up on top. You could do that as well in the 4.5 grams of sodium chloride. So sometimes it's easier in these type of problems, especially if you're given the percentage, to maybe just turn it into a conversion factor, do like a dimensional analysis type of calculation, opposites cancel, and that sort of works really well as well. So again, it really could be any sort of unit of mass, but typically it's grams over grams. And again, we just choose 100 grams of solution because it keeps the top number the same, basically. Yeah. So let's take a look at one here. A solution is made by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of this solution. So we're looking for what is the percent mass to mass here. Okay, let's take a look. So we're looking for our percent mass to mass, which is again the mass of the solute divided by the mass of the solution times 100%. In this case, our 2.5 grams is smaller than 50, so our solute here is 2.5 grams. Water in this case is our solvent. It's the larger part, 50 grams. So we have the mass of the solute. Once again, here we do need to add these together to get our mass of the solution. We do not want to just use the solvent in this case. So that's going to get us, what's that, 52.5 grams is the mass of the solution together. Again, not just 50 here. And we want to make sure we do get that. So now that we have that, our percent mass to mass here would be 2.5 grams of our sodium chloride divided by 52.5 grams of our solution times 100% gives us 4.76% mass to mass. And you can put sodium chloride there if you want, or actually it's calcium chloride. That might be better. Calcium chloride in this case here. Any questions on that one? So again, very common. People just take the solvent. And like I said earlier, very common these questions, they do break that up. So you want to make sure you do get both of them together. Any questions on that one there? All right, I want to try another one here. Concentrated hydrochloric acid contains 37.2% by mass hydrochloric acid. What mass of hydrochloric acid is contained in 35.5 grams of the HCl solution? So see what you come up with here for how many grams of HCl in this case. Okay, let's take a look. Again, we're doing percent mass to mass, so we could use our formula here if we like. One option. Again, it's going to be our mass of our solute divided by the mass of the solution times 100%. Here we have a 37.2% by mass HCl solution. Remember that the name of the solution is the solute. And that means that if I'm looking for how much HCl, I am looking for how much solute. And in this case, is basically the goal here. That's how I know, for example, 35.5 is the grams of the solution. So we do have the 37.2% by mass HCl solution. We do have the mass of the solution, which is 35.5 grams. And obviously here we could look for the grams of the HCl, which is basically our solute. So you could plug and chug into that equation if you like and solve it. You also could, if you weren't sure of the equation, not sure you're going to rearrange it correctly, again, you could take more of a dimensional analysis approach with this. Since we are given the percentage, we could just use that as a conversion factor. So again, what that would mean is we would have 37.2 grams of HCl and 100 grams of solution. Or if you need it the other way, 100 grams of solution would contain 37.2 grams of HCl. So if I kind of take this approach here and start with my grams of solution, 35.5 grams of solution, now I don't have to worry about the formula. And just remember dimensional analysis, opposites cancel. So grams of solution is what I'm looking for, which looks like it should be this one here. And that would get me here 37.2 grams of HCl on top, 100 grams of solution on the bottom, so that the grams of solution cancel. I know this is dimensional analysis, so I'm multiplying the top and dividing the bottom like normal. And that should be it, I think. 35.5 times 37.2 divided by 100. Really bad calculator, but I think it says 13.2 on that screen. 13.2 grams of HCl would be contained in there. So again, here by going a dimensional analysis route, you don't even have to worry about the formula. You don't have to worry about rearranging the formula. Just go opposites cancel, and you know the math that goes with it. Clearly, if you want to do it with this, you have this, you have this. So you would end up with the exact same calculation that the mass of the solute would equal the percent mass to mass divided by, 100% times our mass of our solution, which basically gives you the exact same calculation. So again, maybe a little bit easier. Any questions on that there? Yeah. Now, let's talk about a couple of other sort of percent concentrations. And the next one is volume percent. That is the volume that is used for liquids and gases. Percent volume by alcohol or something like that. This is the percent V/V. It is the volume of solute divided by the volume of solution times 100%. Typically, milliliters and milliliters is very commonly. The nice thing about this one is, unlike percent mass to mass, usually you don't have to worry too much about the solute and solvent being separate. So usually here they'll just kind of give you the mass of the solution or something like that. So you don't have to, or the volume of the solution. You don't have to worry about kind of adding them together like you do with the mass. Again, same idea. If you had a 4.5% by volume here sodium chloride solution, you could also turn it into a conversion factor. That would mean in this case you have 4.5 milliliters of sodium chloride over 100 milliliters of solution. Or of course you could flip it around. 100 milliliters of solution would contain 4.5 milliliters of sodium chloride. So just like we kind of did in that last problem with mass percent, you could also kind of just do more conversion factor if you are given the percent concentration by volume. The last sort of percent concentration is mass to volume percent. So one that kind of deals with both type of units, grams and milliliters. And that is mass to volume percent is essentially like density, basically mass grams over milliliters, right? So kind of the same idea here. So this is percent mass to volume. This would be your mass of your solute, volume of solution, and times 100%. If I can squeeze it in there. Same idea. You take grams of solute on top, divide by milliliters of solution, times by 100. And if you had a 4.5% by mass to volume of sodium chloride, you could turn that into a usable conversion factor, 4.5 grams of sodium chloride and 100 milliliters of solution. Or again, you could flip it around. 100 milliliters of solution would get you 4.5 grams of sodium chloride. So these are three sort of percent concentrations that are sometimes used: mass percent, volume percent, and again, mass to volume percent of a solution. Any questions on those there? All right, so why don't you try one here and see? I think we got one coming up. What is the mass to volume percent of bromine in a solution that's prepared by dissolving 12 grams of bromine in enough carbon tetrachloride to make 250 milliliters? In this case, we're doing percent mass to volume, and that would be our mass of the solute divided by the volume of solution times 100%. And obviously here, this is being dissolved, so that is our solute. Carbon tetrachloride is actually our solvent in this case. And we are making 250 milliliters of solution. So we know the volume of the solution is 250 milliliters. We know the mass of our solute there is 12 grams. All you have to do is divide it at this point. So 12 grams divided by 250 milliliters times 100%. And that's going to give us 4.8 percent. And you could go mass M/V for mass to volume of bromine in this case, right? And again, the units really don't cancel out, but we do kind of leave it as a percentage at the end in terms of it. First off, any question on the calculation? Why is carbon tetrachloride a solvent here and not water? Would water be a good solvent for this? Water would be a terrible solvent for bromine because bromine is Br2, right? And that is a non-polar molecule, right? So nonpolar and water, which is polar, do not mix, right? So they would not make a solution. Carbon tetrachloride, if you draw it really quick without all the electrons, is a symmetrical geometry where everything on the outside is the same, and that is nonpolar as well. So nonpolar and nonpolar, all good, right? So that's going to mix. They're both using dispersion forces, so they're good to go. They're going to mix really well. Again, if you try to put water in there with the bromine, this is what would end up if you did that. Water would be down here and bromine would be up there, not so mixy. Yeah, so they would definitely separate out from each other again because they cannot interact and mix together. Because again, water wants to use hydrogen bonding, which is very, very different. Yeah. Any questions on that? All right, one last one here in this percentages. Calculate the grams of KCl and the grams of water and 225 grams of an 8% mass to mass potassium chloride solution. So we're looking for grams of KCl, which would be this is our mass of our solute divided by the mass of solution times 100%. Remember, our solution is two things, right? It is the solute plus the solvent, which is important in this case because that's how we're going to kind of get to at least the solvent part of it. It's kind of tied up in the solution part of it. So what we do know is we do obviously have the percent mass to mass given to us of 8%. We also have the mass of the solution that's given to us, 225 grams. So again, here you could use the formula or you could do a dimensional analysis. So I'm going to, again, kind of turn this into a conversion factor since I have the percentage given to me. That would mean I have 8 grams of KCl and 100 grams of solution. Or I could use it as the other way in terms of a conversion factor here. 100 grams of solution would have 8 grams of KCl. And again, that obviously comes from here. So I do have our solution. So I'm going to go 225 grams of our solution. Again, just doing dimensional analysis. I don't have to worry about formulas. I want to go grams of solution on the bottom. That's going to be this one here. And that's going to give me 8 grams of KCl and 100 grams of solution. And again, here we're going to multiply the top like normal, divide on the bottom there. And we're going to end up with 225 times 8 divided by 100. I think that says 18. That's going to give me 18 grams of KCl, which is really my solute in this case. First off, any questions on that part of the calculation? Now that I know how much of my solution is the solute, that would actually be this number. Now I could use the solvent and the mass of the solution to actually figure out how much of the solvent in this case is there, which in this case probably would be water. So we know the mass of the solution is the mass of the solute plus the mass of the solvent. And that means that we have 225 grams for our solution. We just calculated our solute, which was 18 grams, plus the mass of my solvent. And now I could just subtract that to the other side. And that'll get me something like 207 grams of water in this case, which is my solvent, would be the mass of my solvent. Questions on that one there? So again, hopefully you can see sometimes dimensional analysis is a good way to go. But again, you could obviously plug and chug into the formula as well. Yeah. Any questions on percent concentrations? All right, the next thing we're going to talk about is, and we touched upon it a little bit earlier, we're doing equivalents, but probably the most common unit of concentration, which is molarity. And molarity is pretty much your go-to concentration for solutions. If you look at any of the bottles probably in lab, they all have a big M on the label, probably with a number in front of it, and that is the molarity of that solution and the concentration of that solution. So the molarity is moles per liter. It is abbreviated with a big M, which stands for really moles of solute over liters of solution are more commonly just spoken of as moles per liter. You should think of molarity as kind of like a formula. You oftentimes are asked to solve for any one of those three things. Molarity, moles, or sometimes volume or liters. So this sort of formula, if you will, is sometimes rearranged. And if you needed liters, that would be moles divided by molarity. If you needed moles, which is a very common calculation, liters times molarity. So those are kind of three ways that it's sometimes used in sort of calculations. Um, if you have a solution that is, we'll stay with the same number there, 4.5 molar sodium chloride, I would highly recommend that when you're doing calculations, especially if you're given the molarity, that you take a more dimensional analysis approach to it and you get rid of the big M. And you should get rid of the big M when you're doing it. You can basically use it as a conversion factor. The number stays with the moles. So this is 4.5 moles per 1 liter is the same thing as that big M. And that would be sodium chloride. And that would be the molarity of it. You could also use this really as a conversion factor. So if you needed to, you could flip it around on its head there and put the liters on top. And you could have 4.50 moles of sodium chloride there. And again, the reason you really should get rid of the big M when you're doing calculation is most people, I will say, when they see the big M, they have absolutely no idea about the volume, where the volume is, that there is even volume involved here. They just think M like moles or something like that, you know. So very commonly people sort of lose track of that part of it. And again, if you kind of see both units there, you should hopefully not lose track of it. And you hopefully won't make a very, very common mistake that a lot of people do make with it. The higher the molarity, the higher the number is in front of the big M, the stronger that solution is, because just math-wise, to get a large number, that means you have a lot of solute dissolved in that solution, which makes it really concentrated. And if you have a smaller number in front of the M, it's more dilute. So if you have a 0.01 molar solution of hydrochloric acid, that is way more dilute than, say, like 18 molar hydrochloric acid. That will burn your fingers right off. No, I'm just kidding. It won't hurt, but it will hurt if you get it on yourself. So the higher the number you see in M in front of it is a lot stronger of a solution and more concentrated. You should really be careful with all solutions, but definitely ones that hit double digits like that, like 14, 12, 16, 18. Those are very, very strong sort of concentrations, especially for acids and bases. Now, when we look at a concentration of a solution that is 1 molar, for example, sodium chloride, it means that we basically have 1 mole of solid sodium chloride that's dissolved in enough water to make 1 liter solution. We talked a little bit about it when we were doing equivalences a second ago, but the way concentration works between like the whole thing and what's swimming around in a solution of this, the ions, are like we kind of saw there when we did that. So again, if we had a 1 molar sodium chloride solution, when that breaks apart, we will get a sodium ion and a chloride ion. And once again, just like we saw before, if we were interested maybe not in the whole thing, but just the sodium ion, again, the way concentration molarity works is you can just do it like a stoichiometry is a 1-to-1 relationship, which means the concentration of just the sodium ions would be 1 times 1, which in this case would be 1 molar sodium ions floating around. And the same thing for our chloride, it'd be a 1-to-1 relationship between the whole thing and the chloride. You would take 1 times the whole concentration, and you would end up with 1 molar chloride ions floating around. So again, if we had calcium chloride, that was 1 molar. When that goes for a swim, it's going to be a strong electrolyte and break apart up into those ions that are going to float around. And that will break apart into a calcium ion, and we will get 2 chloride ions that are floating around. That's what that 2 means, basically. And in this case, it is a 1-to-1 relationship between the whole thing and calcium, which means the concentration of the calcium ions that are floating around in there would be 1 molar. But when we look at the whole thing to the chloride, it is a 1 to 2 relationship. So we do need to multiply the concentration of the whole thing by 2. And that would give us that it is actually 2 molar in terms of chloride in here. Again, if you just got to think about it visually, when this thing goes for a swim, you get 1 calcium ion or 2 chloride ions. You're twice as concentrated in chloride as you are in calcium ions that are floating around. Hence, the concentration here is twice as much in terms of the chloride as it is for the calcium in this case. So again, sometimes you may come across a question that's maybe not interested in the whole sort of ionic compound, and it's maybe just interested in one of the ions that are floating around. That's how you can relate the concentration of the whole thing to each of the ions. By the way, if it broke apart into a 1 to 3, I would multiply the concentration by 3. If it broke apart into 1 to 4, I'd multiply it by 4. So whatever it breaks apart in terms of ions, if you're interested in just the ion concentration, you would do basically times it by however many it breaks apart into. Any questions on that there? So when we do molarity, which is moles per liter, how do we get moles? Well, very commonly to get moles, we oftentimes have to go grams to moles. And that is the conversion we talked about, right? That is the molar mass from the periodic table that allows us to do it. I would say another very common conversion is milliliters to liters and back and forth. So remember, 1 liter is 1,000 milliliters. If you are using molarity in a calculation and you have a volume, you do need to make sure that the volume's in liters before you do the calculation. Otherwise, you will be off. Because if you take liters times molarity, you will get moles. If you take milliliters times molarity, you do not get moles. You get what are known as millimoles, which will probably put you about 1,000-fold off of what you think you're calculating if you don't take that into account. So if you're using molarity by itself, always make sure the volume's in liters. It always needs to be in liters with molarity. If you're just doing molarity problems or anything that involves volume and molarity, it needs to be in liters for everything to work out correctly. All right, so I want to take a look at one here. Calculate the molarity of a solution prepared by dissolving 15.6 grams of potassium bromide in enough water to make 1.25 liters of solution. So again, here we're looking for the molarity, which is moles per liter. So what we want to think about is, do we have any of that given to us? So we definitely have the liters part, right? That's good to go. Again, it's not in milliliters or anything like that. The grams here is not moles, but that's okay because we basically have 15.6 grams of KBr. We can convert that into moles, right? And again, we would need the molar mass from the periodic table. So you would go to the periodic table and find your friend potassium, which is going to say 3910. You'd find your friend bromine, which will say 7990. And we're going to use, again, the molar mass here as a conversion factor to convert our grams into moles so we could calculate the molarity. So KBr, right, is 1 of each. So we're going to go 3910 plus 7990 for our bromine. And that's going to give us a molar mass of KBr of 7990 plus 39. Oops, not that. 3910. There we go. So 119 grams per mole. So remember, molar mass is our conversion factor that allows us to do that. So we're going to, again, dimensional analysis, grams are on top. So we will need the 119 grams on the bottom to cancel and 1 mole of KBr up on top. Again, we're going to multiply and then divide. The grams of KBr will cancel. We'll take 15.6 divided by 119. And that's going to get me here 0.131 moles. That is the top part here that I need to calculate my molarity. Now that I have basically everything that I need, I just need to plug it in there basically and calculate it. So the molarity here will be 0.131 moles divided by our volume that's already in liters. And again, if it was not in liters, but milliliters or some other unit, you do need to convert it to liters before you go into here. And we'll divide our moles there by 1.25. And that will get us 0.105. Now, in terms of the units, they do not cancel. So the number always stays with the moles part, and it's always per 1 liter. And then you put what it is here, KBR. At this point, if you want to, you can convert it back into the big M, and you could write it as 0.105 big M KBR. So either way there is okay in this case. Any questions on those steps? So very, very common conversions used with molarity, grams to moles or moles to grams, and also volume, milliliters to liters, and liters to milliliters. Very common sort of conversion. Any questions on that one there? Let's try one last one here to finish up on what is the mass in grams. Sodium nitrate is required for 2.5 liters of a 0.15 molar of sodium nitrate. I'll give you some numbers here. Sodium 2299, nitrogen here 1401, and oxygen 16. All right, give it a go, see what you come up with here. Okay, let's take a look since we're getting to the end here. We want the mass in grams of sodium nitrate required to make 2.5 liters of a 0.15 molar solution. Again, if you're not sure where to start, clearly molarity is involved, right? So we can kind of think again of molarity kind of like a formula. If we just kind of think about what we have given to us, we obviously have the volume in 2.5 liters. We are given the molarity here of the solution. So really the only thing we're kind of missing from molarity is moles, which seems like a good thing to get, right? Because ultimately we want to get to grams, and we know how to go from moles to grams, right? That's the molar mass that we would use. So that would be kind of the goal here, to get to moles, which would be liters times molarity. And from the moles, we could then go to grams using the molar mass from the periodic table. So in this particular case, our volume is good to go in liters, so we don't have to worry about the conversion of that. We, again, going to take more of a dimensional analysis approach here. Since I do have the molarity given to me, I'm going to get rid of that big M and call it moles per liter. Again, the number stays with the moles, and it's 1 liter. And again, you could kind of use it like a conversion factor, so if you need to flip it around the other way, you could. And since I do have my volume here of 2.5 liters, I know I want to get rid of that. Again, just dimensional analyzing it tells me that is the way I should go. And once again here, I really didn't have to worry about rearranging this equation, right? Because again, I could just kind of do the dimensional analysis, get rid of the units I don't want, keep the units I do want. And again, it tells me now math, I'm going to multiply these guys, right? Which is essentially what we're doing here. And everything's good. And if I do that, that's going to get me something 2.5 times 0.15. It's going to give me, I believe, 0.375 moles, as the liters will cancel, of sodium nitrate. Now at this point, it's really just a conversion between moles to grams. So we do need to go to the periodic table here and add up our sodium nitrate. We have one sodium at 2299. We have one nitrogen at 1401, and we got 3 oxygens at 16 grams per mole. That's going to give us a molar mass 85, maybe. 85. It's going to give us 85 grams per mole as the molar mass of our sodium nitrate. Again, at this point, just a conversion, basically. Still going dimensional analysis, so moles are on top, so I know moles has to go on the bottom here. And grams up on top. And I'm going to times it here by 0.375. I think on this calculator is 31.9 grams, maybe, of sodium nitrate in this case. So basically what that number means is if you took 31.9 grams of sodium nitrate, weighed it out, dissolved in enough water to have 2.5 liters total solution, mixed it really well, you would end up with a solution that has a molarity of 0.15 molar. Any questions on that there? All right, we're going to lay that up there